Hello, everyone. My name is Gül. I'm a postdoc with Pablo De Benedetti, and we are a computational group working in the field of statistical mechanics. One topic that's been a particular focus in our group is low temperature phase behavior of water. There are many interesting things that happen to water at low temperatures, and among those, possibility of a liquid-liquid critical point is definitely one of the most interesting one, as it would explain the anomalies of water. Let's talk a little bit about what are those anomalies. I guess one of the most famous one is the volumetric anomalies of water. Water shows a maximal density at 4 degrees Celsius. This is obviously at ambient pressure, but it is not just that. Thermodynamic response functions of water, such as isothermal compressibility and heat capacity, also show abnormal behavior. As opposed to the response functions of a simple liquid, which would just decrease as temperature decreases, those of water increase as temperature decreases. So this is very curious and obviously abnormal behavior because each response function is associated with fluctuations in a thermodynamic quantity, and even the common sense tells us that they would decrease as temperature decreases. And thermodynamic consistency demands that they cannot keep increasing indefinitely together. They either have to pass through a maximum and then decrease, or they will diverge. And this divergence argument tells us that there must be a critical point, a point of singularity presumably located at deeply supercooled conditions. Like this. According to the critical point hypothesis, there is a pressure where the response functions diverge as temperature decreases. And this pressure would be the critical pressure, and the temperature at which the response functions diverge would be the critical temperature. Tc and Pc together as a state point, they would be the point of singularity, in other words, the critical point. Now, one little problem is this argument is impossible to justify or falsify to the current experimental technology because ice nuclei is too fast before any measurements can be done in the supercooled liquid. So this is one of the reasons why molecular simulations are extremely important in this field because simulations don't suffer from the same problem. I can keep water as a supercooled liquid in my simulations for a long enough period of time to make reasonable measurements. But before showing any simulations or anything, I just want to talk a little bit about the significance of such a critical point. And to understand that, I like to take a look at this phase diagram of water that is for non-crystalline water. So that means it excludes the solid states, but it includes metastable liquid states. The critical points mark the termination of phase coexistence lines. This is the famous first critical point that terminates the coexistence of the vapor liquid phases. And this is where the hypothesized second critical point is. Now, according to the computational findings, this critical point terminates the coexistence of a low density liquid and a high density liquid. Now, I'm telling according to the computational findings because there isn't any rigorous experimental proof that shows the coexistence of these two liquids. But even a theoretical possibility of such a coexistence is very exciting. In 1992, Gene Stanley and co-workers have formulated the second critical point hypothesis based on the series of MD simulations that they have with the ST2 water model. They found an evidence of first order like phase transition from a low density liquid to a high density liquid. And later on, of course, ST2 became a favorite model to study this interesting phenomenon. Like many people work further on ST2 and eventually very unambiguous proofs of metastable criticality and liquid-liquid phase separation have been shown for this water model. But still, there is a fundamental reason why we were not satisfied with these results to say, yes, this must be the scenario in real water. And that reason lies in the model of water, namely ST2. This model is known to overstructure water. What I mean by overstructuring is being overly tetrahedral. And problem with that is that the perfectly tetrahedral particles are already known to have this kind of phase separation. Water, on the other hand, is tetrahedral, but it's much more subtle as opposed to being a rigid three-dimensional tetrad structure like ST2. So once again, we set out the look for an evidence of criticality now in the most realistic classical models of water, like TIP4P 2005. The challenge for these models is that the expected critical point is located at much colder temperatures, so you suffer from a severe slowdown in the kinetics. And the slowdown in the kinetics makes the free energy calculations of a phase separation impossibly challenging, at least for today's computational power. So what we did here is instead of showing the phase separation itself, we just approached to the critical point from higher temperatures. And we unambiguously showed that metastable criticality exists, not only in the model that artificially favors the phase separation at elevated temperatures, but also in the most realistic classical models of water. We used two very independent techniques to show our point. In the first one, we simulated the scattering experiments, and in the second one, we used the modern theory of critical phenomena to drive the order parameter that shows the phase symmetry at the critical point. Well, at this point in my talks, I actually often talk very briefly about the concept of criticality and the universal behavior of criticality. But due to the 15-minute time limit, it's not possible today, and I'm sorry for that. But I will note that there's one key assumption that we made in the beginning of this work, which we later validated. So the assumption is that if second critical point exists in water, it will follow the Ising universality class. So this assumption will come handy in the analysis of my calculations. So this is the first analysis where I mimic the scattering experiments. Here I did simulations at constant volume on the critical isocore, and these are pretty large size of simulations because they need to accommodate for diverging correlation length. And I calculated the structure factor exactly as in scattering experiments. Now, for people who may not know, structure factor would simply be the Fourier transform of radial distribution function, or G of R. And in the reciprocal space or in the K domain, the increased correlations would reflect themselves at the low K region. And that's the reason why I'm zooming in here. You can clearly see the substantial growth in the correlations as temperature decreases. And then I used Ornstein-Zernike formalism, which is a commonly used theory, which is a relatively old theory, commonly used for this purpose. The purpose is to calculate the correlation length and the limiting value of S, or S of 0. The limiting value of S, or S of 0, is linearly proportional with one of the response functions that would diverge as we approach to the critical point, the isothermal compressibility. And correlation length is correlation length. It will, of course, diverge as we approach to the critical point. And they are supposed to diverge following a power law relation as a function of reduced temperature. Tc here is the temperature of singularity, in other words, the critical temperature. And you can see that there is almost an order of magnitude increase in the isothermal compressibility as a function of reduced temperature. Now, I want you to remind you that we assume that the second critical point would follow Ising universality. So I use the critical exponents expected of Ising universality, both for the compressibility and the correlation length, and I simultaneously regress them to obtain a TC that would satisfy the exponents expected of Ising universality. And you can see that I got pretty high quality fits. The lines are fits and the symbols are simulation data. And I got a TC of 173.3 Kelvin. Now, what does it mean? The fact that this is a pretty good fit over an order of magnitude change, it is a very strong support that there is a critical point and that critical point belongs to Ising universality class. Now, this is a very convincing and macroscopically related way of studying critical phenomena, but if you are a simulation person, there are other rigorous statistical mechanical techniques that would allow you to use the modern theory of critical phenomena. For example, finite size scaling. In this particular technique, the system is studied by systematically varying the system size where all of them are finite. The characteristic size of these systems are smaller than the characteristic size of the correlation length. And here I initially intended to walk around the critical points, so I picked my state points to do the simulations accordingly, these blue points. But remember, I don't precisely know where the critical point is. I didn't even know whether there's a critical point or not when we started this work in the beginning. Like, I only have phenomenological guesses where that could be if it exists. So this is a problem because I'm trying to obtain properties of a point that I don't exactly know where that is. So how do I deal with that problem? A rigorous statistical mechanical technique, histogram reweighting. I'll explain the technique a little better in the future slides, but first, I want to show you one of the simulations that I have for the smallest particle size at the coldest temperature, which showed us convincing enough fluctuations between the low density and the high density. But I still note that this is only near the critical point. At the critical point, or very, very close to the critical point, these fluctuations would be more perfectly two-state kind. But this information is still useful. The fact that I have simulations at many other state points like this, I will be able to use the histogram reweighting to recover the density of states at other state points nearby. And that will include the critical point as well. Briefly, with the histogram reweighting, I obtain the histograms of my thermodynamic quantities of interest by extrapolating or interpolating. These are, for example, density histograms, including extrapolations. Now, what I want you to notice is the splitting of these two peaks between the low density and the high density as temperature gets colder. Here I'm actually passing through the critical point without showing a singularity because this is the signature of finite size effects. The singularities would be rounded and shifted. But still, the question is, where exactly is my critical point? Well, given that my system's behavior is consistent with icing, I can compare my system with the perfect icing. For an icing system, there is an expected distribution of the order parameter at the critical point. And here, I'm looking for an analogy to the icing system for my liquid system. What I need to do is comparing the spectrum of my density fluctuations with the known asymptotic expression of the order parameter m for icing. The parameter m for icing is system's magnetization, spin up or down. So in analogy, we thought that our order parameter could be just density, but with a big difference. The two of the states in this case, the low density liquid and a high density liquid, are not symmetric of each other, unlike the spin ups and downs of icing, which are perfectly symmetric. And this asymmetry between these two states yields like a lopsided distribution of the order parameter. But there's a solution brought into that problem, which is called field mixing. The rigorously defined mixing of two fields, density and energy, gives an order parameter, which I will also call M, and that is symmetric for the two phases. I used my histogram reweighting data where I fit the distribution of the order parameter on the expected icing distribution, and this fit would eventually give me a state point where the distribution of the order parameter is closest to the icing. And that point I will call a critical point that belongs to icing universality class. Now, before moving forward to the conclusions, I would like to show you that we repeated all the same calculations for another water model, tip 4P ice. First, notice the fluctuations between the low density and high density. This is a much better example of two-state kind fluctuations because the state point that I did the simulations in this case is much closer to the critical point. And then fit to the icing model, obtain the critical parameters, and then repeated the structure factor calculations as well, the substantial growth in the correlations, and I got compressibility and the correlation length and simultaneous regression. And in this case, I got a TC of 188.6 Kelvin. So bottom line is we were able to show, unambiguously show, from two very independent ways that these two classical models of water have a liquid-liquid critical point, which belongs to icing universality class. Well, this was extremely important to show because presence of a critical point, liquid-liquid critical point, explains the thermodynamic anomalies of water, like I mentioned in the beginning. But the actual significance of this work isn't the reliability of these two models. With this work, we essentially showed that it is not just ST2 that has a metastable criticality. Instead, these two classical models, which are widely regarded as to be among the most realistic ones, also have a liquid-liquid critical point. Still, it doesn't necessarily conclude anything about real water, but it definitely brings us one step closer to the real water. This work has just been published in Science this summer. I hope you enjoyed as much as I did. Finally, I'm blessed to work with this couple of people in this work. One of them is my postdoc advisor, Pablo De Benedetti. The other one is his long-term collaborator, Francesco Shortino from University of Rome. Finally, I thank all of you for paying attention, and I will be more than happy to take any questions in the question and answer session. Thank you.